yesterday, so we're going to go through, just review this again. All right, girls, have a seat. Caitlin, sit down. All right, so speed. We talked about this earlier. Speed is the distance that something is traveling divided by how long it took to go that distance. Okay? So it's a unit of distance divided by a unit of time. Our formula, speed equals distance divided by time. You could abbreviate S equals D over T. That's fine when we're solving these problems. So if a bird travels 100 kilometers, that's the distance. And it took 5 hours, that's the time.
Second bird.
Okay. We always follow our steps with our solving problems. Write the formula, substitute in the numbers, and then give an answer with units. Okay, we did this yesterday. Now the units of speed are always going to be dependent on the units you had in your problem. So the distance in this case was in kilometers. The time in this case was in hours. So our units of speed in this example is kilometers per hour. Okay, if I have a rocket that's traveled 1,400 meters in 30 minutes, again, you calculate the speed. We give our formula, substitute our numbers. What is our answer? 46.7 meters per minute. So again, it depends on the units in our problem. And did I tell you guys yesterday this is incorrect?
Yeah, it was supposed to be seconds.
Yeah, well, it should be, yeah. Because a rocket, I can probably walk 46.7 meters. I certainly could per minute. A rocket is going to be traveling much faster.
Did you make this error?
No, it started carrying that error. All right, now, when we calculate this, what we're calculating really is what we call the average speed. Because obviously a rocket doesn't begin immediately traveling at 46.7 meters per minute. It takes time for it to go from a stop to that speed. And so that's called the average speed. Okay? When something is moving at a constant speed, it means its speed is not changing over time. Like, I don't know if you ever have been in the car and paid attention, your parents are driving on the highway, they may put the car in cruise control mode. Where basically you're going at a certain speed, you press a button, and then you can take your foot off the gas, and it's going to keep you going basically at that speed until you hit the brakes again.
Or the gas button.
Yeah. All right, now these are two words that often are used interchangeably, but they're technically not the same thing. Velocity and speed are slightly different. Okay? But many people will use them interchangeably. So velocity is similar because it has the speed, but you have to add one piece of information to truly get a velocity. And that information is what? The direction the object is moving. So if you're being asked for a velocity to be technically correct, you need a direction as well as the speed that the object is moving. So, for example, I may say a train's velocity could be 130 kilometers per hour south. That's the velocity, because I've given the distance. If the speed changes, the velocity is changed. But also, if the direction changes, its velocity also changes. That train turns and starts heading east, then it has a new velocity.
So basically it's got one extra piece of information.
Yeah, it's got an extra piece of information.
Wait,
Direction.
if it like turns this way, it's still 130 kilometers per hour east.
Yeah, but it's different because it's not south anymore, so it's a different velocity.
It would be something.
All right, another example. If a boat's going due south at 50 kilometers per hour, then starts heading east, has its velocity changed? Yeah, it's changing direction, so its velocity is changed as well.
But the 50 km has.
Right, because that's its speed, but not its complete velocity. Sometimes we combine velocities. Okay, you've probably experienced this before. For example, if you've been in an airport where there was moving walkways, or an escalator, that when you go up the escalator, if you walk with the escalator and you look around, how do you appear to move?
Really fast.
Really fast. And I'm sure some of you have been goofing around and went the opposite direction on the escalator.
It's hard.
And what does it feel like as you look around?
It is.
Yeah, you're staying in the same place. In this case, you have to combine the velocity of the escalator or the moving walkway with your velocity as well. Is that just a side note? Has anyone been to Washington, D.C. and taken the metro? Some stations, like in out towards Maryland, near DuPont Circle, have these huge escalators. The tallest escalators, I believe, maybe in the world or in the United States, are in the Washington, D.C. metro subway system. You have to go down these huge escalators because the subway tunnels are very deep in the ground. Anyway. No, but it takes you like, I don't know, 30, 40, 50 seconds to get down this long
Which is
escalator.
a long time.
Yeah. All right. So another example: if a man's on a train, the train has a velocity of 200 kilometers per hour due west. If the man is walking forward in the train at 5 kilometers per hour, what is his overall velocity going to be, Nicholas? Okay. The train is traveling 200 kilometers per hour due west. He is walking with the train 5 kilometers per hour. The combined velocity is 205. So in actuality, he is moving westward at 205 kilometers per hour.
Although he can only go that speed as long as the train is.
Yes, you have to combine the velocity of the train with his velocity. If you've ever done this, been on a train, you look out the window, if you walk forward, or if somebody was watching you from the outside, you'd be moving very quickly as you're walking forward in that train. Brandon?
What if you walk the opposite way?
So let's say that he's going back to his seat. The train's velocity has not changed. It's still 200 kilometers per hour due west. But now he's walking back to his seat at 5 kilometers per hour. What would his velocity be in this case?
190.
Thomas?
195. Kilometers per hour. Kilometers per hour. Due west.
Speak up.
Good. 200 kilometers per hour. He's walking backwards 200 kilometers per hour. His overall velocity is 195 kilometers per hour due west.
But he's walking east.
True. But his overall velocity from the outside world, if you looked at him, which direction would he be traveling in? Still west.
He's going forward but backward.
But usually the fastest, like say there's two speeds, and usually the fastest speed would that be the one that?
Yes. What if the train slowed down, was coming to a station at 5 kilometers per hour, and then he was walking back to his seat? What would his velocity be?
East west.
0.
0 kilometers per hour.
Oh, now I get it.
All right.
10.
And no, be
Acceleration now. So we need to talk about acceleration, which you guys sort of came up with the definition as our question of the day. So in acceleration, we're looking at the change in the velocity of an object over a period of time. And so to know, the information you need to know to calculate acceleration is the change in the speed of the object and how long it took it to change speed. Anyone think you could come up with the proper formula to calculate the acceleration of an object?
No.
Matt?
D over T times V.
Not quite, no. Habib?
Speed equals velocity over time.
What was that?
Speed equals velocity over time.
No. We're talking, I want to know acceleration, a formula for acceleration. Do that? quite. You're getting there though. Brandon?
Acceleration equals the new speed minus the original speed, divided by time.
Correct. Okay, so we can write this many ways. Often, technically, the correct formula is acceleration equals Vf minus Vi over t. Final velocity minus initial velocity over time. We're going to just simplify it a little bit. We're going to say acceleration equals the change in velocity divided by the time it took to change. That's exactly what Brandon said. So if we have a rocket that goes from a stop at 0 kilometers per second, accelerates to 20 kilometers per second, and it took 10 seconds for that to take place, what would its acceleration be? There's going to be one problem I would guess you're going to have here. Sophia?
2 kilometers per second.
Okay, you're close. Kimberly?
22 seconds.
No? Me?
Negative 2 kilometers per second.
What?
Negative 2 kilometers.
No, it's accelerating. It's positive acceleration. The problem is not with Sophia's calculation. The problem is with what?
How she labeled
Her units. So if you think about this carefully, you should be able to figure out what the unit should be. Right?
2 kilometers per millisecond.
No? So first we have our formula. Let's write. Acceleration is change in speed over change in time. Put our numbers in. So the change in speed was 20 kilometers per second.
Isn't it changing velocity?
Yeah, but we often omit the direction, so really speed would probably be more accurate. Divided by the time it took to change that speed, 10 seconds. Anyone want to take one more guess before we move on, Nicholas?
2 kilometers per second.
What was it?
Per second.
Okay, yes. It's 2 kilometers per second per second. Does that make sense?
No.
Yes.
So if you think about what is going on, every second, this rocket's speed is increasing by how much?
2 kilometers
2
per
kilometers?
second.
Kilometers is not a speed.
2 kilometers per second.
What? 2 kilometers per second.
Every second that goes by, its speed increases 2 kilometers per second.
Per second.
So that's where we get kilometers per second per second.
So kilometers per
So-
second.
All you get
But then got to do
Per second, yes. Every second, it's increasing 2 kilometers per second.
What would 2 kilometers per second per second per second?
Okay, how can it increase 2 kilometers per second per second?
Because, okay, let me say in a more familiar unit. If your car is traveling at 10 miles per hour
Yeah.
and you increase to 20 miles per hour, and it takes 2 seconds to do that,
20 miles per hour per second.
what was your acceleration?
10 miles per hour.
10,
Miles per hour.
Okay, 2.
10 miles per hour
Per second.
per second. Every second that went by, your speed increased 10 miles per hour.
To be 10 miles per hour per second.
That would be it.
Well, so you just combine two.
You combine whatever units are in your problem.
Oh,
Is there a way to
So
show?
kilometers per second per second.
Is there a way to show that when it
Every second.
Yes.
Is there a way to show when it would stop?
What do you mean?
Like, say you're in
If
a
you have
car.
deceleration, yeah, when the speed equals 0. All right, another example. So if a person, I don't have this one solved on the overhead, but person on a motorcycle accelerates from 7 kilometers per hour to 37 kilometers per hour, and it took 2 minutes. What was her acceleration? Again, the key here, the difficult part is the units on these problems. Natalie?
15 something, 15 kilometers per second.
No, look at the problem.
Per minute.
Look at the problem.
Okay.
So her speed was increasing. What was your number?
30 kilometers in 2 minutes.
Okay. So what would the units be? So 30 divided by 2, you got 15.
Yes. And then 0. I don't know what the time is.
Nate?
15 kilometers per hour per minute.
Yes. 15 kilometers per hour per minute. So every minute that went by, her speed on a motorcycle increased 15 kilometers per hour.
Oh, I get it now.
No.
Something inside here.
Excuse me?
Just combine the units.
It's combining units. And if you think about it, it should make sense. You're increasing your speed over a certain amount of time. You went 15 kilometers per hour faster, but every minute you increase.
Yeah, because I was thinking that I was thinking that 2 kilometers per second, it was just gonna be like a distance.
Yeah, or if you say it differently, you could say each minute her speed increased 15 kilometers per hour.
Yeah.
All right. Acceleration can be negative. What does that mean?
That
Deceleration.
No.
Decreasing speed.
Its speed is getting smaller, slowing down.
Deaccelerate.
That's also called deceleration. Negative acceleration is sometimes called deceleration. All right, now things are going to get interesting.
I love slime.
So we're going to be looking at 2 different types of graphs.
That looks like the Pringles.
And what's going to be difficult sometimes is that we have 2 types of graph and different lines and slopes. They mean different things depending on which type of graph you're looking at. So let's start with these graphs. These are graphs that show on the y-axis the velocity of an object. And on the y-axis, did I say that wrong? On the y-axis show the velocity. On the x-axis they show time. So this shows the velocity of a boat at various times over 16 minutes. All right, so on these types of graphs, what does the slope represent?
Acceleration.
Okay. Sophia?
constant speed.
Constant speed?
Constant speed is flat.
Not constant speed. Ryan?
Acceleration.
Acceleration. If you think about it, if this line, what is happening to its velocity? It's increasing. That's what acceleration is. A change in
Oh,
velocity.
I was talking about the flat.
Sophia, when the line plateaus, what does that indicate? That it's traveling at a constant speed. This boat is traveling at the same speed, which is not changing. Now, what does a steeper slope mean on these graphs? Julia?
Up, not straight up.
So the steeper the slope, what does that mean?
Faster. Slower. Time.
No,
Deceleration.
not faster, not slower. Brandon?
A bigger, acceleration.
Yes, that it has a greater acceleration. Speed is increasing. This is the same graph. Now we just have a few questions. This is kind of what your homework's going to be like. So, what was this boat's speed between minutes 2 to 10? 2 minutes, 2 to 10. What was this boat's speed? Natalie?
Is that 8 meters per second?
Yes, it was 8 meters per second. Between time 2 and time 10, it was 8 meters per second. Oh, really? What's that? Yes, usually. Was its speed constant during this time?
Yes.
Habib, how do you know?
Because it was a plateau.
It was a plateau. The graph was flat, meaning constant. All right. This one's a little tricky. What was the boat's acceleration between minutes 0 and 8? What was its acceleration? Figure it out. Matt?
8 miles per second per minute. Or
No.
not. 4 meters.
Ryan?
8 meters per second per minute.
No.
Oh,
Sophia?
4 meters per second.
No. Habib?
4 meters per second.
Nope. Brandon?
2 meters per second or per, 2 meters per second.
Nope. Ryan?
8 meters per minute per second.
Nope. Skinner?
1 meter per second per minute.
Very good.
Oh.
All right, so let's look at this. All right, so what do we need to know to do this? Change in velocity over change in time. What was it between 0 and 8 minutes? What was the change in velocity? 8. It was started at 0 minutes, it was 0. At 8 minutes, it was 8 meters per second. What was the time that it took to do that? 8 seconds.
What is 8 minutes?
I'm asking you between 0 and 8. The total acceleration in that time period. 8 divided by 8 is 1. Units. Meters per second per minute. What was its velocity at 8 minutes? What was its velocity at 8 minutes, Brian?
8 meters per second.
Yes. When was this boat accelerating at the greatest rate? What was the highest rate of acceleration for this boat? Nicholas?
0 to 2.
0 to 2, how do you know?
That was slow as the steepest.
Yeah, steeper slope.
Next slide.
All right, now, what's different about this graph?
It doesn't have a graph.
Yeah, but besides the lack of numbers,
Yeah, it's.
is it conveying the same information?
No. Ish.
No.
No, it is not.
What is this a graph of? Distance versus time. Not speed versus time. So, what does this section A represent? What's happening at A? Habib? Change in speed? Nicholas?
Increase of distance.
Okay, so its distance is increasing over a period of time, which means the object is moving. Okay? Is it moving at a constant speed?
We don't know.
We don't know.
We do know.
At B it is. Yes.
Why, Kimberly?
No, it's not.
It's a straight line. Therefore, it's covering the same distance for each time interval. It's moving at a constant speed. What does this plateau represent? So a plateau, Thomas?
Oh, it's staying in the spot.
Yeah, it is stopped. Because what's happening to its distance? Nothing, it's just staying where it was. It's the same distance from its starting point.
Like, say it's a car and they're accelerating, and distance by then, they keep moving like the tire on the ground.
No, because this is not showing the speed of the car, it's showing the distance it is from where it started. So if its distance isn't changing, it stops. What does C represent? I guess it's not. Ryan?
It's going backwards.
It's going backwards. It's decreasing its distance. A steeper slope represents what? What does a steep slope on this graph represent? Natalie?
More distance covered,
Which would mean what?
acceleration.
No? If you cover a longer distance in a smaller amount of time,
Speed.
yeah, the steeper the slope, the faster the speed. Okay, so that should make sense here. What is this graph showing? What is this graph here showing?
Distance in meters or something.
Right, but what does the bend in the line represent? Nicholas?
An increase in distance.
Yes, but how? Its distance is increasing, you're right. How is it increasing? Matt?
A sudden increase?
I don't know. Thomas?
It's not an equal, it's not staying constant,
So what's happening?
so it's changing speed,
How?
slower and faster.
No. It's not getting slower or faster. Peter?
It's going faster at a rate.
Speeding up. It's accelerating because the line is getting steeper, meaning it's covering a greater distance for a smaller time interval, showing acceleration. Because again, think about what's a flat line mean? Stop. What does this line mean?
Faster increase the speed.
Yes, but how? Slow. What is this? What does this mean?
Fast.
What does this mean?
Very simple.
Infinite speed. What does this graph show?
Decrease.
Deacceleration.
Deceleration. The object's doing what?
Slow down.
Slowing down. Alright, you draw the line showing up. Oh, it's already on your paper, isn't it? A biker accelerating from a red light. What happens to the slope? He's accelerating. Gets steeper. Then they reach a constant speed. What happens to the line?
Stays
Straight.
straight.
Got it? No problem?
It's hard.
I like this.
Okay, turn to page 303 in your binder.